Unit 16, Acid-Base Equilibria, pages 209 to 218, Calculating pH. We'll start with calculating the pH of strong acids and bases. Because a strong acid will ionize 100%, then the concentration of the acid is equal to the concentration of the hydronium. Kc is large for strong acids, and the equilibrium mixture consists entirely of products, entirely of these two. We assume that the amount of reactants remaining is negligible. So, strong acids completely ionize, which means whatever amount of acid you have initially is also the amount of hydronium that will be produced. So here's an example. Example 16.66. Given a 0.040 molar nitric acid solution, what is the pH? So we assume that when nitric acid is placed in water, that we're going to have a transfer of hydrogen from the acid to the water, which is going to leave us with NO3-, and this is going to become hydronium. This is a 0.040 molar concentration, which means that this produced is 0.040 molar because it's a 1-to-1 ratio, which generally all acids will be, and it's a 100% ionization. So if that's how much I started of the acid, then that is how much hydronium I'm going to produce. Therefore, I can take the negative log of this hydrogen ion value in order to get the pH. Negative log 0.040, and that is going to give us a 1.40. Notice that we have 2 sig figs, so we want our pH to have 2 decimal places, so it would be 1.40 is the pH. Strong bases will completely ionize to products, so for calcium hydroxide we have to take into account its stoichiometry. When it ionizes, we get 1 calcium ion and 2 hydroxide ions, so we have a 1-to-2 ratio. So that means that the concentration of calcium hydroxide, we have to do the stoichiometry to figure out the concentration of our hydroxide, which is essentially going to be this concentration times 2. So example 16.67. What is the pOH for a 0.011 molar calcium hydroxide strong base solution, and then what is the pH? So first we'll write the equation for calcium hydroxide. We'll get 1 calcium ion and 2 hydroxide ions. This is 0.011 molar, and so since this is a 2, then the concentration of this will be 2 times 0.11 molar. So we can take the negative log of 2 times 0.011 molar, and that would give us a pOH of 1.65. Remember, we actually have 2 sig figs here, so 2 decimal places, so 1.66 would be the pOH. To find the pH, we would do 14 minus 1.66, and that would give us 12.34 as a pH. And that should make sense because this is a strong base, so we should have a strongly basic pH. Polyprotic acids are acids that dissociate and can yield more than 1 proton. So we're talking about H2SO3 or H2SO4 or H3PO3 or H3PO4. We have more than 1 hydrogen in the acid. So the first hydrogen would ionize and have a Ka value, but then the second hydrogen is going to have a negligible ionization compared to the first. So the majority of the pH is based on the first ionization and not so much on the second ionization, which is a lot smaller of an amount of hydrogens that are produced. The Ka of 6.4 times 10 to the negative 8 in the second step is so small compared to the first step of the reaction that it's negligible compared to the first. It is clear from the values of Ka that the H plus from the second step is negligible compared to the first. This is true for most polyprotic acids. So usually the pH is going to be calculated just based on the first ionization, and then we just don't bother with the second one because it's just too small to even really worry about. The key feature about weak acids and bases is that they do not completely dissociate. Since the reaction is not complete, concentrations must be found from the equilibrium expression as discussed in chapter 15. So if you want the pH of an acid, weak acid or pOH of a weak base, you're going to have to do an ice table first. Weak acids and bases do not completely dissociate. In fact, equilibrium often lies far on the reactant side, and so you have a K value that is much less than 1. Example 16.68. Calculate the pH of a 0.20 molar hydrocyanic acid solution with a Ka value of 4.9 times 10 to the negative 10, a very small Ka value. So first you want to start by writing the equation. Hydrocyanic acid plus water is going to yield, we're going to transfer the hydrogen from hydrocyanic acid, leaving us with cyanide as the conjugate base and hydronium as the conjugate acid. Since we're going to be calculating the pH, we really only care about how much hydronium are we going to make. Remember that the water is in the liquid phase, so we don't actually include it in our equilibrium expression. So I'm going to write my law of mass action over here. The Ka is going to be equal to the cyanide times the hydrogen ion concentration, remember these are the same, divided by the hydrocyanic acid concentration. And we have a Ka value equal to 4.9 times 10 to the negative 10. So when we set up our ice table, we have a 0.20 molar solution to start, and we assume that these are 0. This will be minus x, this will be plus x plus x. So at equilibrium, we have 0.20 minus x, x, and x. So we need to find out what is this value of x, because once we know that, then we can take the negative log of that value, since it's the hydrogen concentration, and therefore figure out what does the pH equal. So I'm going to write up my law of mass action. 4 times 10 to the negative 10 is equal to x times x, which is x squared, over 0.20 minus x. We are going to use the 5% rule, which means because the K value is far smaller, very, very small, way smaller than 1, as long as it's times 10 to the negative 4 or smaller, then we can consider this right here as a negligible part of this reaction or equation. So now I'm going to multiply both sides by 0.20, and that'll cancel this, and then I'll take the square root of both sides, and this will take care of that squared. So x is going to equal, let's do this math, 9.8995 times 10 to the negative 6. So now that I know what x is, it just so happens that x is equal to the amount of hydronium that I have produced. So if I take the negative log of x, then I would get the pH, which is 5.004. It's important to always validate this approximation that we do, meaning validate that ignoring this x is within the 5% rule. So to do that, you're going to take x, which is this value here, you divide it by the initial concentration of the original acid, 0.20, and then times 100, and as long as this answer is 5% or less, then it's okay for us to do this approximation. But if it's not, then we cannot ignore this minus x, and we would have to redo this calculation here using the quadratic formula. So we have 9.8995 times 10 to the negative 6 divided by 0.2 times 100, and we get a value that's very small, 4.95 times 10 to the negative 3, so far below 1 even. So it's a very small percentage that ionized, and so this is actually a legit approximation that we can do. So an important problem-solving strategy, you must always investigate the magnitude of the equilibrium constant to determine whether the quadratic equation must be used or if an approximation can be used. In general, for concentrations of greater than 0.01 molar, the KEQ must be less than 1 times 10 to the negative 4 for an approximation to be valid. To check the approximation, we're going to take the constant, we're going to take x divided by the initial concentration times 100, and as long as that's less than 5% or 0.05, if this is less than 0.05 or that is less than 5%, then it's a valid approximation. Example 16.69, 0.15 molar solution of hypochlorous acid is prepared and the pH is measured to be 4.17. So we know what the pH is. What is the Ka for HClO? So let's first write our equation. Hypochlorous acid plus water yields, the hydrogen is going to go from here to here, leaving us with ClO negative and hydronium. Remember that water is a liquid and therefore is not included in your equilibrium calculation. The law of mass action is going to be Ka equals hypochlorite times hydrogen ion or hydronium divided by hypochlorous acid. And then what we want to know is, what is this K value? So we know that initially we had 0.15 of this, 0 and 0 of that. We know that the change would be minus x plus x plus x. And so we know that at equilibrium this would be 0.15 minus x, this would be x, this would be x. So we actually have been given the information to determine the amount of hydronium, or what x is. And that can be determined using the pH, which equals 4.17. Because we know the pH, we can determine the hydrogen ion concentration by going 10 to the negative 4.17 in our calculator. So when we do that, we get 6.76 times 10 to the negative 5. And that's going to be our molar concentration of hydronium. So now that is what x is equal to. So I can actually plug that in for each of my x values and then plug these numbers into my equation to find the Ka. So this is 6.76 times 10 to the negative 5. This is 6.76 times 10 to the negative 5. And when I do 0.15 minus that number, I get 0.14993. So now I will plug those into my law of mass action, and essentially this is going to be 6.76 times 10 to the negative 5 squared. This times this is just that squared, divided by 0.14993. And when I do this math, I get a Ka of 3.048 times 10 to the negative 8. And that is my equilibrium constant. Example 16.70, we have a 0.14 molar solution of acetic acid and calculate the percent ionization using this Ka value. So it's a weak acid, so we're going to have to do an ice table. Put it in water. Transfer your hydrogen from your acid to the water. We're left with the acetate ion and the hydronium ion. Remember, this is a liquid, so it's not included in our equilibrium calculation. We start with, let me write my law of mass action over here. Ka equals acetate times hydrogen over acetic acid. So now that I have my law of mass action here, I do have also the Ka value, 1.8 times 10 to the negative 5. Notice that it is smaller than times 10 to the negative 4, so we're going to be allowed to use the approximation. So here's my ice table, and we start with 0.14 molar of this, 0 and 0. We'll have minus x plus x plus x, and then at equilibrium we'll have 0.14 minus x, x, and x. So we want to solve this for x, first of all. And then once we know what x is, since this was our initial amount, the percent ionization is going to be equal to my value for x divided by the initial concentration, 0.14, times 100. And then that answer is going to be my percent ionization. So here, we're going to put in our 1.8 times 10 to the negative 5 equals x squared over 0.14 minus x. Because this value is very small, we're going to make our approximation that this is negligible. So I'll multiply both sides by 0.14, and if I take the square root, that'll cancel this, and the square root of both sides would give me the value for x. which is 1.587 times 10 to the negative 3. And so now that I know my value for x, that can be plugged in here, 1.587 times 10 to the negative 3, divided by the original concentration times 100 is going to give me a value of 1.13%, which is the percent ionization. So when you put this in water, only 1.13% of it will actually turn into ions, and the rest will remain the original acetic acid. Also, because this is less than 5%, it validates that when we did this approximation here, canceled out that minus x, that means that it is okay to do that because we are below 5% ionization. If we had not been below 5%, then you would not be allowed to do this, and you'd have to solve using the quadratic formula. Here's your note card for this section. You can pause the video and copy it down. The larger the Ka, the stronger the acid will be. The larger the Ka, the lower the pKa would be. That's just an FYI for another section. Strong acids are going to have a large Ka value, and weak acids are going to have a small Ka value. To find the pH of a strong acid or strong base, you can just take the negative log of the concentration originally given of the acid or the base. But to find the pH or pOH of a weak acid or weak base, you have to do an ice table first, and then once you know what X is, then you can take the negative log of the hydrogen concentration to get the pH. Approximations are X divided by the initial concentration of the acid times 100, and as long as it's less than 5%, then it is a valid approximation called the 5% rule. If the percent ionization is not less than 5%, then the problem has to be solved using the quadratic formula.